Hello, Year 13s. This is just a short presentation introducing you to sequences at A level. Really, a lot of this is very similar to sequences at GCSE. It's just, if you ask, we have a slightly more grown-up way of notating it. So, whereas before at GCSE you would have worked with sequences which look something is 3m minus 2. Now, this is a linear sequence, yeah, and we've decided to call it nth term. And what's handy about nth term definitions is straight away I can tell you the 100th term in the sequence. The 100th term in the sequence is going to be 3 times 100, 300, take away 2, 298. So this kind of definition, by the way, I would describe this as a deductive definition. Yeah, there's lots of different ways of describing these kind of things, but I would describe it as a deductive definition. I'm going to put on the other side here, I'm going to put an inductive definition because, well, one second, I need to sneeze. Sorry, got a bit of a cold. Okay, so that's a deductive definition, yeah? There is another way of defining it. There is the inductive definition, yeah? Now, this is kind of the mistake that students make when you're giving an nth term for exactly this sequence. Like this sequence, by the way, at A level, our kind of grown-up way of notating this now is not with nth term. You might see it, maybe they'll use it, but I'm write something like this: U subscript n. Yeah, and that's because sequences are defined to be any list of numbers which go like this: U1, let me make that one a bit clearer, U1, U2, U3, U4, and so on and so forth, all the way up to whatever, UN maybe, yeah? That is the sequence that you're looking at, yeah? That's the way we think of it anyway in our heads. So if you want to know the first term, that is U1, and that is 3 times 1 minus 2, which is of course 1, yeah? I'm sure you remember anyway from nth term GCSE that that's just a sequence 1, 4, 7, 10, 13, and so on and so forth. Now, what often happens when you ask a GCSE student to give you the nth term for that sequence, they either get it right and they say, oh, it's just a 3 times 2, so it's 3n minus 2, or they get it wrong and they do something like this. They think, well, nth term, that's got to be n plus 3, yeah? Well, you can see where they're coming from because they're telling you how to get from one term to another. They're saying, oh, I just need to add 3 to get to the next term. Now, the only mistake they've really made is just with the notation. They're confused about the notation. And what they've really given is what I would describe as an inductive definition. It does have other names, though, and I'll tell you the other names in one second. What they should have said was u little n plus 1 equals un add 3, yeah? Then I would agree with them completely because what they're saying then is to get to the next term, all you need to do with the last term is add 3. And that is absolutely right. And we call that, by the way, it's called an inductive definition. You can call it a recurrence relation. You could even call it an iterative definition, yeah? It's an iterative. If you do computer science, that might be a bit clearer why that's an iterative definition. When things iterate in computer science, they go around in like a loop, or in some way they in some way refer back to the same step. Here we're doing exactly the same thing. We're just saying to get to the next term in the sequence, you just take the last term and add 3. And by the way, that is absolutely equivalent to saying un equals un minus 1 add 3. They're the same thing. It's the same answer. You could even say it's the same as un minus 2 equals un minus 3 add 3. They're all the same answer, and you know they would all be accepted, although we tend to give one of the first two really. So yeah, we've got two different ways of defining a sequence there. The deductive definition, which is un equals 3m minus 2. And we've got the inductive definition, which is un plus 1 equals u little n plus 3. Notice those are all subscripts as well, yeah? And those are both the definitions for this kind of sequence, 1, 4, 7, 10, 13. Let me just make that a bit clearer. I'm just showing you that there are two different ways of expressing the same sequence, 1, 4, 7, 10, 13. Yeah, let's try it with another sequence. Let's pick another linear sequence. So let's say I had the linear sequence, I don't know, let's do one which is slightly more interesting. Let's go backwards. 30, 28, 26, 24. So we've got a sequence again, yeah? And remember, this is supposed to be representing U1, U2, dot, 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 all the way up to UM. M being the nth term of the sequence. It is exactly the nth term. Well, I'm sure you remember that UN is simply 32 minus 2n. I hope you remember that. It's basically because it's just like the negative 2 times table, but starting from 32, because then when n is 1, you get 30, but when n is 2, you get 28. When n is 3, you get 26. And so that would be a deductive definition, or they'll probably refer to it just as an nth term definition of a sequence. If you wanted to give an inductive definition, something I forgot to point out up here, that alone is not enough. You also need the first term. So they'll also give you, if they're giving you an inductive definition of a sequence, they'll also give you the first term, or maybe the second term, or the third term, but normally the first term. Then that uniquely defines that sequence. Okay, so for this one, un equals, un plus 1 equals un, take away 2. Yeah, in other words, to get to the next term, what you do is take the last term and take away 2. We also need the first term, so U1 is 30, yeah? And that's the difference between these deductive definitions and these recurrence relations, yeah? The recurrence relations are, I always say that the definition, a recurrence relation definition, is never really as handy as a deductive definition. And that becomes real obvious when you are thinking about programming these sequences, I think. Because if I wanted to work out the 100th term in either of these sequences, the definition on the left is way easier to use than the definition on the right. The definition on the right, you're going to have to find the first 99 terms first before you find the 100th term. And in that sense, the inductive definition, if you like, isn't quite as good. Yeah. Okay, so let's just take a few examples. Well, can I do a famous example now? I'd quite like to show you why we use inductive definitions, and it would be nice to show this with the Fibonacci sequence. This might come up, I suppose, but I think it's unlikely. But yeah, we'll see. Now, I hope you're aware of the Fibonacci sequence. Let's have a look. Let's write it down. Okay, so you've got, sorry, I'm just dropped my pen there. Let's do Fibonacci now. And I'm still going to break it up into inductive and deductive definitions, just so you see they're just two ways of defining the same, the same sequence. Okay, so Fibonacci looks something like this. 1, 1, 2, and it depends actually. Some people like to start at 0. I think we should possibly start at 0, maybe. Let's have a look. Yeah, let's start at 0. Okay, 0, 1, 1, 2. You get basically the next term by adding up the two previous terms. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 13, 21, 34, so on and so forth. Yeah. Now, the inductive definition is way easier to give than the closed form definition, yeah, or than the deductive definition. The inductive definition is simply this: un plus 2 equals un plus 1 plus un, yeah? And you could say the first two terms this time. U1 equals 0, U2 equals 1. Now, you'll never have to do this, but the deductive definition looks like this. Are you ready for this? This is going to blow your mind. 1 over root 5. Straight away, it looks weird. Multiplied by 1 plus root 5 over 2 to the power of n minus 1 over root 5 multiplied by 1 minus root 5 over 2 to the power of n. And here you can see why the inductive definition can sometimes be really, really handy. The deductive definition is better if you're programming it into a computer, because we could easily now find with this one the 100th term of the Fibonacci sequence just by plugging in n is 100. But what we could not do is actually, oh yeah, by the way, this one starts with an extra 0, as if you start with 2 zeros, I think, because that way when n is 1, you're going to get 0 popping out of that, I think, or maybe not, actually, maybe not. Let's try it. Let's have a look. If we wanted to find the first term, we're going to let n equal 1. I think we start from 0, you'll get 0 basically. But if you get u1, let's just have a look. 1 over root 5 1 plus root 5 over 2 to the power of 1, which is just like that, 1 over root 5, 1 minus root 5 over 2 to the power of 1. You're going to get 1 over root 5. I'm going to factorize that out. Then I can do 1 plus root 5 minus 1 minus 5 all over 2. And what do I get there? The root 5s, I get 2, I get root 5, I get 1. Yeah, so obviously that one starts off with first term 1, and if you like, u0 is 0. Yeah, so there you go. The sequence does work as well. Try, u4 or u5 in your calculator and watch the Fibonacci numbers pop out. It's incredible. It really is. Anyway, you don't have to worry about that. You certainly don't have to learn the deductive definition of the Fibonacci sequence. It's just a little bit of enrichment I'm showing you there. I just think it's amazing how the inductive definition is so simple, but the deductive definition is so complicated. Anyway, what comes up in this first exercise? Well, recurrence relations and inductive definitions and everything like that, but also convergent, divergent, and periodic sequences. So some sequences converge. What does it mean that for a sequence to converge? Sequences converge if they're heading towards a number. Sequences converge if they get closer and closer to a number. They can oscillate around that number, yeah? So let me just show you a couple of examples. Let me give you an example of that. You could have the sequence, I don't know, un equals 2 plus 1 over n. Yeah. I wonder if you can tell me what number that is converging on. Have a little think. Pause the video if you like. Well, what we could say is as n tends to infinity, 1 over m tends to 0. Yeah. In other words, as n gets really, really, really large, 1 over n gets really, really, really small. And therefore, un is going to converge on 2. And so that sequence converges on 2. You do get sequences, though, which oscillate around a number, going one above, a little bit above, a little bit below, but they only converge if they're getting closer and closer and closer to the number. They never take a step back. They're always getting closer and closer and closer. You never find a term which is further away than the previous term. They should always be getting closer and closer and closer. Divergence is the opposite of this. Divergence is where it definitely isn't heading towards a number, and therefore it's going towards positive infinity or negative infinity. It's just getting bigger and bigger and bigger, or more negative. Yeah. So divergence is like the opposite of that. Sequences diverge if they head to positive or negative infinity. Yeah, then they're basically going, getting larger and larger and larger, or smaller and smaller and smaller. And finally, I'm going to give you one more definition of a sequence. Some sequences are periodic. Not all, but some are. Now, if a sequence is periodic, you can describe its period, which just means how long it takes to complete a cycle, or a circle of numbers. So let me show you an example of a periodic sequence. Let's have un equals 3 plus negative 1 to the power of n. Yeah. Now, if you start looking at the first few terms, u1 is 3 minus 1, which is 2. u2 is 3. Now, negative 1 squared is going to be positive 1, and therefore that's going to be 4. u3 is 3 plus negative 1 cubed. I'm sure you can see what's going on here. That's going to be minus 1, so that's going to be 2. And so that sequence just goes 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and it's got a period of 2 because it takes 2 terms, it just repeats 2 terms. Just look at the length of the sequence which repeats itself. So this is just length, this period is 2 because it just takes 2 values. A bit like, you could say sine that for the sine curve, its period is 360 degrees because every 360 degrees it repeats itself. It's the length of the recurring sequence. So its period is 2. Okay, and so those are 3 sequences you might want to be aware of. Now, let me also go through a couple of examples. So let's take a couple of examples. I'll just take a couple of examples from the review exercise so I don't tread on your toes with exercise 4a. I'm just going to pinch a couple of examples here straight from the review exercise. Where is it? So yeah, let's say I'm sure you'll be fine with writing down the first few terms. That'll be fine. Oh yeah, let's do find the nth term, or yeah, they'll probably say find the nth term if they want the deductive definition of the sequence. And let's do a tough one straight away. Let's do this one. 1 over 2, and then we can have 3 over 7. Then we can have 5 over 12. Then we can have 7 over 17, dot, dot, dot. If you have something like this, don't stress because you've got a linear sequence on the top and a linear sequence on the bottom. Now notice I'm not going to write nth term, I'm going to write un and be slightly grown up about it. On the top, you've simply got the sequence 2n minus 1. On the bottom, you've simply got the sequence 5n minus 3. And hence that's the answer. You know, like if you're just doing nth terms on those at GCSE and I gave you just the numerators or just the denominators, you'd find it really quite straightforward, I'm sure. So yeah, that's how that works essentially. Now let's try and find the limit of a convergent sequence, because this is something I think you do need to be shown. So let's just find a sequence where we're trying to find the limit of a convergent sequence. Let's have a look. Yeah, let's do, okay. Un plus 1, so that's my first example. Here's the second one. Given un plus 1 equals 1 over un plus 2, find the value to which the sequence converges. Okay, if we're going to do this, yeah, we've got an inductive definition here. But what you've got to realize is if the sequence is converging, then for large n, or can I write as n tends to infinity, un plus 1 should be roughly equal to un, because it's supposed to be converging on a limit, which means that once n gets really, really, really large, the next term is basically the same as the last term because they're getting very, very close to a limit. Well, now we can use this idea by just saying, okay, if the limit is, say, x, let the limit be x, because then x equals 1 over x add 2. In other words, when n is sufficiently large, it's close to infinity, the next term should equal 1 divided by the last term plus 2. Now it's just about solving this equation, times 3 by x, subtract, and then solve. So I'm going to solve that by completing the square because it just looks perfect for completing the square. X minus 1 squared minus 1, which is minus 2. And so this one looks to be converging on something which I think is called the silver ratio in maths, actually. 1 plus or minus root 2. It's not the golden ratio, which is 1 plus or minus 1 plus root 5 over 2. That came up earlier, actually. That was in the Fibonacci closed form definition. 1 plus root 5 over 2. That's the golden ratio. Well, this is called the silver ratio. I think it comes up a lot in maths as well. You don't have to worry too much about it, but yeah, you can try it now if you like as well. Take your calculators out, and this should work with any first term. Yeah, if we let u1 equal 5, yeah, take your calculators out and just keep iterating that step. Yeah, do 1/5 plus 2, but basically, but the way to do it very quickly on your calculator, you can use that fast calculator method. Press 5, press equals, and now press 1 divided by answer add 2, and then just press equals 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 equals, I'm doing it loads and loads and loads and loads of times, and I end up with 2.414 on my calculator, which is 1 plus root 2. And so one of those values, it will always converge to one of those values, and yeah, the value it converges to is 1 plus root 2. Okay, right, I'll leave it at that because I think you'll be fine on this, but please do get in touch on the Maths Help Desk if you do get stuck on any of the questions from exercise 4A. Keep up the hard work, and I will see you all very soon. Okay, bye-bye.